Hi everyone, welcome back. So I hope you're well. In this video, we're going to work out this sample final. This is sample A. I will leave a link in the description box of the PDF file of the test. That way you can work it out on your own before you dive into the video. There are not too many questions on this test. There are only about, as you can see, there are 10 problems. So please work them out before you check into the answers. Let's go ahead and start. All right, so for the first question, we're going to show that the following limit does not exist. So we're going to do the path test. We are going to approach along two different paths and show that the limit are unequal. So let's pick a path. Let's go along the path. Let's choose y equals 0. So that's just the horizontal line, y equals 0. So if y is equal to 0, I'm going to go ahead and replace these variables y with 0 and then take the limit. It becomes a single variable limit problem. So we will take the limit as x approaches 0 of x squared cosine of x, y is 0, so it's just cosine of x over x squared because y is 0. And here with further simplification, these two variables will, these two terms will cancel. So you'll have the limit as x approaches 0 of cosine of x. And now you can do the direct substitution. This is cosine of 0. Cosine of 0 is 1. So along this path, our limit is 1. Now let's take a look at along another path. For instance, let's go with y equals x, because that will also pass through the point 0, 0 that we're approaching. So if y is equal to x, then we have the limit as x approaches 0. So I'm going to replace each y with x, then simplify. So we have x squared cosine of x plus x, because y is x, all over x squared plus x squared, because y is x. And then I'll simplify this. So we have the limit as x approaches 0 of x squared times cosine of 2x over x squared plus x squared, that's 2x squared. Now here, again, we can see that we can simplify. X squared will cancel out. So this will leave us with the limit as x approaches 0 of cosine of 2x over 2. And now plug in, we can substitute 0 into x. This will be cosine of 2 times 0. Well, that's just going to give us 0 over 2. Cosine of 0 is 1. This limit is 1/2. So along this path, we got 1/2. Since these two limit values are unequal, we can say that therefore our limit as xy approaching 0, 0 of x squared cosine of x plus y, the original problem, over x squared plus y squared does not exist. So that's our final conclusion for this problem. Okay, moving on to the next problem. So here we want to fill in the blank with real numbers to make the following statement as precise as possible. So at some point, xo, yo, the partial derivative respect to x is 3, and the partial derivative of f respect to y is -4, then, well, this is the directional derivative of f at that point xo, yo in the direction of a unit vector u. We know by definition that the directional derivative of some function f in the direction of a unit vector u at some point xo, yo is always between magnitude of the gradient of f evaluated at po, and on the left side we have negative magnitude of the gradient of f at po. So if you need to review this concept, go ahead and review directional derivative section. You should be able to pull out this information. Now, how do we compute the gradient of a function of two variables since we're only given partial respect to x and y? So note that the gradient of f at some point po, so in this case, we're given xo, yo, so those are the coordinates. I'm going to go ahead and write that. At xo, yo, it's going to be the partial of f respect to x at xo, yo, partial of f respect to y at xo, yo. So that's our gradient of a two variable function. So we're given what these components are. So this is given to be 3. and partial of f respect to y given to be -4. So I'm just going to substitute them. So our gradient of f at this point would be 3 comma -4. Now, if you want to find the magnitude of this gradient vector, gradient of f at xo, yo, we know by definition, this will be the square root of sum of each component squared. So this is 3 squared plus -4 squared. And this will give us the square root of 9 plus -4 squared. That will be 16, which will be square root of 25. That would simplify to 5. So that's really what we're going to substitute right here. This is +5, and this will be the -5. So as you fill in the statement on these two blank, you'll fill it in with, here you'll have 5, and here you'll have -5. So that will be the statement of this particular example. Moving on to number 3, for this problem, we have a cylindrical solid enclosed by x squared plus y squared is equal to 4, z equals 0, and z equals 5, and it has a mass density of this function. We're going to set up to find the mass and z coordinate of the center of mass, and we don't have to do any of the integrals. So we're just going to go ahead and set it up. So hopefully you can imagine how this looks like. So let's suppose this is our cylinder. And let's suppose this is the bottom. And let's just suppose, of course, it continues on. So I'm just gonna make a stop at z equals 0 and z equals 5. So if I put in my axis right here, so here's the z-axis. Here is our x-axis, and here is our y-axis. So this is z. So z equals 0, well, that's this plane right here. So this is z equals 0. And let's suppose z equals 5 cuts it off right here. And this is z equals 5. So the solid we're looking at is this right here, just between these surfaces. Okay, so this is our solid. Now, if you were to set up an integral for mass, it's going to be a triple integral. So the mass, we know by definition of a solid, let's call this solid E. So this is going to be the triple integral of this solid E of our density function times dV. That's the definition. So we're going to set this up using, I guess we can use rectangular coordinates since we don't really have to figure out how to solve it. So you can set it up using cylindrical or rectangular. I'm going to go ahead and set up rectangular first. So let's see how this looks like. So in rectangular coordinate system or Cartesian, you can say that the mass is equal to this triple integral of the density, which is given as 8 minus tangent inverse of z squared, that is given to us right here, of dv. So I'm going to pick, let's see. So our first most in our integral will be bounded by z. So z goes from 0 to 5. So that will be the bound on z. Then the outer two integral, I can set it up about in any order I really want. So let's go ahead and take a look at what the projection looks like in the xy plane of radius 2. So that's what we're going to get. So that means I can set it up in rectangular. So you can do a vertical cross section or horizontal. So I'm going to set it up vertical. So I'm going to treat it as a type 1 region. So you'll have x going from constant to a constant. So we know this is -2 and this is 2. And y is going to go from a function to a function. So we need to know the equation of this circle. Well, the equation of this circle is right here. That's x squared plus y squared is equal to 4. And I'm going to go ahead and solve for y. So you're going to have y is equal to plus or minus the square root of 4 minus x squared. Now, if you split it up into two set of equation, the upper half of the circle will be the positive square root of 4 minus x squared. The bottom half will be y equals negative square root of 4 minus x squared. Now, y, you can set it up this way. The bottom function is going to be the negative square root of 4 minus x squared, and the top function will be the positive square root of 4 minus x squared. Now, if you set up your integral, we're going to do dy dx because I'm treating the region as a type 1. So my bound on y would be a function to a function. So I'm going to go ahead and give myself some room. So our bound on this integral will be from negative 4 minus x squared to a positive square root of 4 minus x squared. And x is going to go from negative 2 to 2. So that's how you set up the mass. So this will be our setup in rectangular. Now, since we have a polar region, we could actually set up the outer 2 integral as a polar. I mean, in 3-dimensional, we can think of it as a cylindrical coordinates. So another way you can also set up mass. So you could set up in cylindrical coordinates as a triple integral. So we'll have a bound on r, theta, and z. So we know z is going from 0 to 5. So that's not going to change. And our integrand has the density function 8 minus tangent inverse of z squared dz. Now, for cylindrical coordinates, we have r, dz, dr, d theta. So we need to find our bound on r. That's going to go on this integral, and then theta will go on this integral. So let's take a look at our region on the floor again. So this is a circle of radius 2. That means r is going to go from 0 to 2. That's the bound on r. And then theta is going to go on entirely. So we'll have from 0 all the way around to 2 pi. So 0 to 2 pi will be the setup for theta. So there you have it. This is the setup in cylindrical coordinates. It looks much easier than rectangular coordinates. And I think evaluating it will also be quite simple, but we're not doing it for this problem. The next thing we want to set up, so we have done mass. So that's done. Now, z-coordinate of the center of mass. So the z-coordinate of the center of mass, that is z bar, and this is going to be 1 over the mass times the moment about the xy plane. So we know the mass, that's this integral right here, or the one in rectangular. So we just need to find the moment about the xy plane. So the moment about the xy plane, it's going to be, again, triple integral over the solid E of z times the density times dv. And you can, again, set it up in rectangular or cylindrical, but it looks like cylindrical is easier. So I'm going to go ahead and use that. So our moment about the xy plane would be the triple integral. So first integrand, we have 0 to 5. Then the next, we have 0 to 2. Those are bound on r. And then from 0 to 2 pi, those are the bound on theta of z times density. Density is 8 minus tangent inverse of z squared. Then we have r, dz, dr, d theta. So that will be the moment about the xy plane, which means our center of mass, the z-coordinate of the center of mass is going to be 1 over m, which is whatever that integral gives us, times this integral right here. So I'm just going to go ahead and copy this, and that will be our final answer for this particular example. So this will be the z bar, or the z-coordinate of the center of mass. All right, so number 4, we're going to find and classify the critical points of this function. So we need partial derivatives. So first, let's find partial of f respect to x. So we're going to differentiate f respect to x. You'll have 3x squared minus 12, and then we're going to set it to 0. So that would give us our partial of f respect to x. We can find the x-coordinate of the critical points if we have any. So you have 3x squared minus 12 equal to 0. You'll have 3x squared is equal to 12. Divide by 3, you'll have x squared is equal to 4. Take the square root on both sides. You have x is equal to plus and minus 2. All right, so that's our x-coordinate. And then we take the partial of f respect to y. So again, going back to my equation, take the partial respect to y. You will have 6y minus 6, and then we're going to set it to 0. So that will give us y is equal to 6 divided by 6. That will be 1. All right, so our critical points, so let's call them CP, are -2, 1, and we have 2, 1. So that's our critical points. Now we need to classify them. That means we need to go ahead and test our Hessian at these points. So hopefully you remember what the Hessian is. The Hessian h of x comma y, by definition, this is equal to partial of f respect to x, x partial of f respect to y, y, so it's the second partial, minus the mixed partial, the second mixed partial of f squared. That's the definition. Now we're going to go ahead and compute our second partial derivative. So we're going to take the partial derivative of this respect to x, and then also this one respect to y, and then we mix it up. So we take partial of this respect to y. So let's go ahead and compute them. So partial of f respect to x, then take the partial again respect to x. That will be 6x. And then partial of f respect to y, take the partial of y again. You're going to have 6. And then we're going to take the second mixed partial, f sub xy. That's going to give us 0. So again, I'm looking at these formulas and taking their next partial derivatives. All right, so let's go ahead and try the Hessian for the first point, -2, 1. So I'm going to test what is our Hessian at the point -2, 1. So you have 6 times x is -2, f sub y, that's 6, minus this is 0. So this is going to give you a negative value. So this will give us a negative value. So if your Hessian is negative, immediately we know that's a saddle point. So this will imply that the point -2, 1 is a saddle point. So that's how we classify this one. And then for the next point, we have 2, 1. So let's check the Hessian at the point 2, 1. So again, I'm plugging into my Hessian. This is 6 times 2 times 6, and then minus 0. This is a positive value, which means if the Hessian is positive, and if we know our second derivative, x f sub xx is also positive, so this is also positive at that point, that means we actually have a local minimum. So since this is positive and our f sub xx is also positive at this point, this implies that the point 2, 1 is a local minimum. So that is how we classify them. And you can plug them into the original function to get the z coordinates, but I think this is okay. All right, so here's number 5. We are going to evaluate this double integral over the region T of 2x plus 6y, where T is the triangular region in the xy plane with corners at the origin 0, 4, and 2, 0. Let's draw a picture. So it is always best that you try to draw a picture. So we're on the first quadrant. So here is L 0, 4. And let's suppose this is 2, 0. And the origin is right here. So looking at this triangular region. So this is our region of integration, that's T. So let's see how we can set it up. So you can treat it as a type 1 or type 2. I think either is really fine in this case. So the double integral over the region T of 2x plus 6y dA. So I'm going to set it up as a type. I want to set it up as a type 1. So we're going to do a vertical cross sections like this. We'll have a top and a bottom. So we need to know the equation of this line. So we got the 2 points. You can find the slope and figure out the equation algebraic way. And you'll see that the equation you'll get is y equals -2x plus 4. I believe that's the equation of that line. So I'm going to describe T as the setup point in xy such that, so let's find the bound on y. So we're doing as a type 1 region. So our dA is going to be dy dx. So we're going to replace dA with dy dx. That means my y will go from function to a function. So the lower limit of y is 0, and the upper limit is the equation negative 2x plus 4. And x will go from a constant to a constant. So we'll go from 0 to 2. So that's how I'm going to describe this region. This is a type 1 region. So our integral is going to be set up this way. So the inner integral will be from 0 to the line 2x plus 4, negative 2x plus 4. And the outer integral is going to go from 0 to 2. And our integrand, we have 2x plus 6y dy dx. So that's how I'm going to set this up. Okay, now we proceed with integration. So the integration is not so bad for this problem. It's actually very straightforward. Let's see how this will come out to be. So I will integrate first this respect to y. So we're gonna go ahead and just hold on to the outer integral 0 to 2, just work out the inside. So maybe I'll do that with a different color. Okay, here you go. So if I integrate 2x respect to y, there'll be 2xy. If I integrate 6y respect to y, I'm going to get about 3y squared. And then we're going to evaluate this from 0 to negative 2x plus 4. Then we integrate that respect to x. Okay, so maybe I will put this in a different color, just like this. All right, so again, focus right here. This is what we're going to simplify first before we integrate again. So go ahead and plug in the upper limit in place of y. So we're going to plug in the upper limit in place of y right here and simplify. So we have our integral from 0 to 2 of 2x times y, that's negative 2x plus 4, plus 3 times negative 2x plus 4 squared. As you plug in 0 as a lower limit, you're going to get 0. So that's not needed. Just write it like that. All right, so I'm going to simplify it a little bit more before we start integrating. So let's take a look at this side that we need to expand. So this we need to expand before we start integrating. So if you expand that, you're actually going to get 4x squared minus 16x, I believe, plus 16. And then we're going to multiply this by 3. So that's going to give us, so hopefully you can follow through with me. This is going to be 12x squared minus 48x plus 48. So that's where I'm going to replace for this piece right here in the integrand. And here I'm going to distribute this out. So here's what we get. We have, so moving on right here, got the integral from 0 to 2 of, so 2x times negative 2x, that's going to give us negative 4x squared. And then 2x times 4, that's going to be positive 8x. And then I'm going to write the piece in red that we just got. This is positive 12x squared minus 48x plus 48. Okay, I hope you got the same thing as me. Then we have dx. Okay, let's combine some like terms. So if I combine some like terms, I'm going to get the integral from 0 to 2 of 8x squared minus 40x plus 48. So by combining some like terms, that's what I get. Now we're ready to integrate each piece respect to x. So this is going to be 8 over 3 x cubed minus 20x squared for the second term. In the last term, we get 48x. Then we're going to evaluate this from 0 to 2. I hope you got the same thing as me. And now we can plug in the upper limit. The lower limit is 0 and everything has x, so it's going to give you 0. So we have 8 over 3 times 2 to the third minus 20 times 2 squared plus 48 times 2. And just a little bit of simplification, this will give us 64 over 3 minus, I believe this will be 80 plus a 96. And then if you add them up, you're going to get 64 over 3 plus 16. I think this is a nice answer to leave at. Or if you want to go further, I think this will give you 112 over 3. So something like that. All right, we continue to number 6 now. So for this problem, we're going to find the volume of the solid between the xy plane and the surface, this one. And here we can actually just draw these right here, we don't have to really draw the surface because we know z is going to go from the lower limit for z would be 0 and the upper limit will be 12x squared y plus 4. So those are the bound on z. And in the xy plane, here's what we're going to draw. So here's our xy plane. And so we have x equals -2. So that will be the vertical line right here. Let's suppose that's x equals -2. X equals 1. Let's suppose that's this right here. So this is x equals 1. And then y equals 2. Let's suppose this is y equals 2. And y equals 4. That would be right here. Okay. So the region we're looking at is between these curves. So that's this right here. This is the region we're looking at. Okay, so let's take a look at how we're going to set this up. So our volume, we know that this is going to be the triple integral over the solid E of 1 dV. So here I'm going to set up a dV as, now this region that we have, you can treat it as type 1 or type 2, but I think I'm going to go with type 1 again. So I'm going to set up like this. So we have a top and a bottom for the bound on y, and left and right we have the bound on x. Since they're all constants, you can actually, it doesn't really matter how you set it up. So I'm going to go ahead and set this up as the triple integral. So our most inner integral will be the bound on z. That will be 0 to the surface 12x squared y plus 4. The z, then our next bound will be on y. Y goes from 2 to 4. And then the next bound will go on x. So we'll have x go from -2 to 1. So that's how I'm going to set up the integral. So let's go ahead and work it out. So we have the integral of 1 respect to z. That's going to be the so we have the double integral -2 to 1 and then 2 to 4. If I integrate 1 respect to z, that will just be z. And then we're evaluating this from 0 to 12x squared y plus 4. Once we finish that, then we integrate respect to y, and then we do integration respect to x. Okay, so I hope this makes sense. So we plug in the upper limit of integration. We have 12x squared plus y plus 4 times y plus 4, plug in for z. So you're going to integrate from -2 to 1, and then from 2 to 4 of 12x squared y plus 4. We're going, and then when you plug in 0, you're going to get 0, so that wouldn't be needed. And then we do dy first and then dx. Okay, so now we're going to go ahead and integrate this respect to y first. So we're going to have the outer integral -2 to 1. So if I integrate 12x squared respect to 12x squared y respect to y, I'm going to have 12x squared y squared over 2. And then 12 and 2, that will simplify to 6. And then integral of 4 respect to y, that will just be 4y. And now we can evaluate this from 2 to 4. And then we integrate this respect to x. Okay, so now we evaluate this from 2 to 4. So we're going to place, we're going to evaluate it in place of y. So first we plug in the upper limit of integration 4. So we have the integral from -2 to 1 of, so you have 6 times x squared. So we're replacing y with 4 first. So that'll be 4 squared, that's 16, plus 4 times 4 minus, and then 6x squared times 2 squared, that'll be 4, minus 4 times 2. All right, and then we integrate. So a little bit of clearing before we continue. So so if we do 6 times 16, that's going to give us a 96. So we have the integral from -2 to 1 of 96x squared plus 4 times 4. That's going to give us a 16 minus, so 16, 6 times 4, that'll be 24 x squared minus 8 dx. So you can continue to simplify. So it looks like these two can be combined so as these two. So with further simplification, before we integrating again, so we do 96 minus 24x squared. That's going to give us 72x squared, and then 16 minus 8, that's going to be positive 8. And now we integrate respect to x. So 72x squared, if you integrate the respect to x, you will have 72x cubed over 3 plus 8x. And now we can evaluate this from -2 to 1. Okay, so let's go ahead and simplify. So 72 over 3, that's going to give us 24. So I'm just going to write that here. Now we plug in the upper limit of integration first. So we got 24 times 1 cubed, that will be 1, plus 8 times 1, that will be 1, minus 24 times -2 cubed, and then minus 8 times -2. Okay, so this will give us, so if I do 24 plus 8, I'm going to get 32 here. -2 to the power of 3, that's going to be 8. And then if you do 8 times, -8 times 24, we're going to get positive 192 plus -8 times -2, that would be 16. So if we now add up all of these constant, we're going to get, I believe, about 240. So that will be our volume to this problem. For number 7, we're given a field. F is given 2 components, and we want to find the work done along the path R of t, which is given also as 2 components, with t being in the interval from 0 to 1. And it may help to notice that F is conservative. Okay, so we can use the fundamental theorem of line integral, but first we need to check that F is conservative. So to check that, now since F is a function of 2 variables and you have 2 components, you can label them. So here I'm going to go ahead and label the first component of F. So this component, we always call that M. And this component, we always call that N. So that's just the labeling. So you want to check the following for a conservative field, that if you take the partial of M respect to Y, this should equal partial of N respect to X. So let's check that. So partial of M respect to Y. So that's going to be, so we're going to differentiate this only because this doesn't have a Y. So product rule here. So differentiate that respect to Y, you're going to get 2e to the 2xy, and then plus 2y times, so you're going to get 2x times e to the 2xy. So a little bit of clearing. So this is 2e to the 2xy plus 4xy e to the 2xy. So that's our m sub y. Now we take the partial of n respect to x. So here we're going to focus on this right here. Take the derivative of that respect to x. This is going to be 0. So differentiate 2x, you're going to get 2 e to the 2xy plus, now keep 2x, differentiate e to the 2xy. So that's going to be 2y e to the 2xy. 2y, so I'm sorry, I meant to write 2y. Now clearing things up, so we got 2e to the 2xy plus 4xy e to the 2xy. All right, so as you can see, these two things are equal. So therefore, this implies that F is conservative. Now, since it is conservative, now we can use the fundamental theorem of line integral. That means to find the work along this path from 0 to 1. So we know this is the integral along the curve C of F dotted with dr. And we know this is going to be the potential function little f. So we're going to evaluate f at r at b minus f of r of a. So we need to figure out where is our potential function little f is, and then we're going to evaluate the little f at the endpoint of the curve. So let's go ahead and do that. So just make this a little bit smaller so you can see. So I need to find the starting point of the curve. So the starting point of the curve, we're going to call that r of a. So that would be r at 0 because we're given the interval from 0 to 1. So here you're going to plug in these points. So the starting point, it's going to be plugging in 0 in place of t. So you'll have 0 for the ith component and 0 for the jth component. And then so the ending point of the curve, starting point, ending point. So that's going to be the curve evaluated at B. So for this curve, we're looking at 1 when t is equal to 1. So again, plug in 1 in place of R, in place of t for each value. So you're going to get 1 plus 1, that would be 2. For the first component, second component, you're also going to get 2. Just double check that. Okay. Now we need to find the potential function. So this is the first step. Now, second step, let's find the little f, which is what we're going to call the potential function of this field. So pretty much I'm going to take my component m and integrate respect to x. So for this problem, our component m is right here, 2y e to the x 2xy. So we have the integral of 2y e to the 2xy, and the next term is 2. So that's our m. Now we're going to integrate this respect to x. So if you integrate this respect to x, y is treated as a constant. So the first term will give you, so 2y, that's just a constant. You have e to the 2xy divided by the constant, so that'll be 2y, plus integrate to respect to x, that would be 2x. And if you simplify, you're going to get, so these terms will cancel out. You're going to get e to the xy plus 2x. So that's one of the piece. Then the next thing we're going to do, take n, integrate that respect to y, and then we're going to collect each unique term. That'll create the potential function f. So n happens to be from the problem, it's this right here, that's n. So 2x e to the 2xy plus 4y. So we have the integral of 2x e to the 2xy plus 4y. We're integrating this respect to y. So if I integrate this respect to y, as you can see, this will give you e to the 2xy plus 4y squared over 2. So that's 2y squared. All right, so our potential function, little f of xy, it's going to be this term, and this term plus a constant c. So you don't have to repeat this since we already got that from integrating m respect to x. So you'll have 2 e to the 2xy plus 2x plus 2y squared plus c. So that's our potential function, and now we're going to evaluate. So now we're ready to find work along that path using the fundamental theorem of line integral. So here we go. Our work, it's going to be given by this formula. So we're going to go ahead and set up the integral. So we're going to integrate from t equals 0 to 1 of the gradient of f dotted with dr by the fundamental theorem of line integral. So this will be the little f of r at 1 minus the little f at r at 0. So now we plug in. So at r of 1, we know that this we found out to be right here, 2, 2, and r of 0 is right here, 0, 0. So we evaluate. So this is going to be f of 2, 2 minus f of 0, 0. And evaluate this at this function right here. So we're going to get our work along that path. So this will be equal to e to the power of 2 times 2 times 2 plus 2 times 2 plus 2 times 2 squared plus c minus, now the lower limit, we have f of 0, 0. So I'll plug in 0 for each x and y. So you'll have e to the 0 plus everything will be 0. So you'll have 0, 0 minus plus c. So as you can see, this will give you e to the 8 plus 2 times 2, that's going to be 4. And then 2 squared, that's 4 times 2, that's 8. And then plus c. And e to the 0, that's going to be minus 1. And then we have minus c. So these will cancel out. Now we can simplify. This will be e to the 8 plus 11. So that will be the work done along that path by the field. All right, so we're on number 8 now. For this problem, let's see what we have. So let S be the sphere of radius 5, center at the point 1197. Think of the sphere as a globe with the North Pole at point with the largest z value. Let C be the curve, which is the equator of S. Right, so this is important. Travel clockwise when viewed from above. Okay, this is important. So first thing we want to do is parameterize the curve C. So let me give you a picture, a rough picture of what's going on here. So suppose this is our X, Y, and Z plane. So let's just say this is our three-dimensional space. And I'm just going to roughly sketch the sphere. So we have a sphere right up here. So in X unit, you go 11, and then Y 9, Z 7. So perhaps somewhere right here. Let's just say that roughly it's right there. And you have a sphere of radius 5. So let's just suppose this is the sphere. Just suppose that. Okay, so that's the sphere. Let me just make it look like a 3D picture. Okay, so that is what we're looking at. So the center of the sphere is going to be 11, 9, 7. So this level right here, this is z equals 7. Okay, and we have this curve that's tracing clockwise. So this is the curve C that's at the level z equals 7. So it's going clockwise. So the direction is this way. Okay, so that is curve C. Let's parameterize it. So for part A, we're going to parameterize curve C. So let's describe it as a vector valued function R of t. So since it's clockwise, we're going to use x to be sine, y to be cosine. Now, since it's centered at a different point, not at the origin, so our you can think of x component will be, so the radius is 5, sine t plus the x coordinate of the center, that will be 11. And then y would be in r cosine t. So r is 5, cosine t, the center will be for the y coordinate is 9. And the z doesn't change. We're at the level 7. So z is going to be the constant 7. So let's write it out as a component wise. So you'll have 5 sine t plus 11, 5 cosine t plus the y coordinate of the center, and z is 7. So that's our vector valued function, or that's the parameterization of the curve C, which represents the equator of S. Okay, now we're also gonna let t go from 0 to 2 pi, so it's gonna go all the way around. So t will range from 0 to 2 pi. So that's the answer to part A. We just parameterize the curve C. For the second part, we want to know, so if f is defined this way, this is our definition for f. All right, so the line integral along the curve C, this is a closed curve of f dot the unit tangent head ds. This is going to be the integral, so the curve is parameterized by that. So it'll go from 0 to 2 pi of f dot. So this is really, you can, so let me just give you one more definition. This is really just the line integral along curve C of f dot dr. So we need to figure out what is f. Well, f is right here. It's already been given to us. So we're going to evaluate f at our parameterized curve C, r of t. So you can also write this as the integral from 0 to 2 pi of f evaluated at r of t dotted with r prime of t dt. That's how we evaluate. So we need to go ahead and take the derivative of this because that will be r prime of t. So note that r prime for this particular problem, r prime of t component wise will be 5 So differentiate the first component, that'll be 5 cosine of t, and the second component, negative 5 sine of t, z component, the derivative of 7 is 0. Okay, so now also find f at r of t. So f is given to us, the one I highlighted in yellow right there. So we're going to sub in our components. So we know this is the x component, this is the y component, and that's the z. We're going to sub them into our field f. So f of r of t, that's going to be, let's write it component wise. So we'll have cosine of y squared. So y is 5 cosine of t plus 9. So hopefully you can see this. I'm just going to make it a little smaller. Okay, so this is going to be 5 cosine of t plus 9 squared, because that's what f told us to do. The second component is ln of x. Our x is 5 sine t plus 11. And the z component, we're going to have a z that's 7 minus 3. So that would give us 4. All right, so that's what we're going to substitute. So this will be our representation for f of r of t. We're going to plug that right here. And our prime of t, we're going to plug that right here. And we have the integral set up. So let's continue. So our answer to B is continuing right here. So we'll have the integral from 0 to 2 pi of f of r of t. So this would be cosine of 5 cosine t plus 9 squared, ln of 5 sine of t plus 11, 4. We're going to dot that with our prime. That'll be 5 cosine of t negative 5 sine of t and 0 dt. So that's the continuation of our integral. Now, if you want, you can really leave it right here or perform the dot product. I'm going to go ahead and leave it right here so it doesn't look too messy. All right, so that's the setup for the second part. All right, here's number 9. So we're going to sketch the region of integration and change the order of integration. So that's what we're going to do for this problem. So let's write down what we're given. So these are the bound on y, these are the bound on x. So we know y is going from x over 3 to square root of x, and x is going to go from 0 to 9. And we want to change. So we're going to have to figure out how to represent the same integral. We're changing the limit of integration into dx dy. So that's what we want to do. So let's figure out what will be our limit of integrations for x and y. So we're going to sketch the region of integration. So here's our xy plane. So this is x, this is y. So so this curve right here, this is a line. So let's suppose we have a line x over 3. So something like this. So this will be y equals x over 3. And then the second curve is y equals square root of x. That's going to look something like this. So this is y equals square root of x. And this intersection, this happens at x equals 9, which means the y value of this intersection is actually 3. You can plug them in and check. So our region of integration is this right here. So initially we're given vertical type 1 region, and you want to convert that to a type 2 region. So we want to perform integration this way. So we want to do as a type 2. So we want to describe the region R as a set of points in xy such that we want to find x to go from a function to a function and y to go from a constant to a constant. That's what we want to do. So we know y is going to go from here to here, 0 to 3. So the next thing is to figure out where will x go from. Well, x is going to go from left to right, so from this function to that function, but you need to solve them in terms of y. So we're going to isolate each functions in terms of y. So this multiplied by 3, you'll have 3y is equal to x. And this one, you square both sides, you'll have y squared is equal to x. So there you have left and a right. So this is your left, this is your right curve. So that means x is going to go from the left curve, which is the square function, and the right curve, which is the line. So 3y. So that's how you find your bound on y and x. Okay, so let's go ahead and substitute them right here. So x is going from, the lower limit is y squared, the upper limit is 3y, and y is going to go from constant 0 to 3. So that's how you switch the limit of integration. Now let's proceed with the integration. So hopefully you got this. So continuing on here. All right, so the work for the integration will continue right here. Okay, so integrating this is actually very easy. This is a very nice one to continue on with. So I'm going to integrate first this respect to x. So we're going to have the integral from 0 to 3. If I integrate that respect to x, I will have 6x squared over 2. That will be 3x squared. Evaluate this from y squared to 3y. And then we're going to integrate that respect to y. Okay, so now let's plug in the upper limit of integration. So you'll have 3 times 3y squared. So I think I want to write it this way. Minus 3 times y squared squared. And then we integrate that from 0 to 3 respect to y. So with little simplification, so 3y squared, that's going to be 9y squared. So we do 9 times 3, that would be 27. So we have the integral from 0 to 3 of 27y squared minus 3y to the 4th dy. And now we integrate. So 27 y to the 3rd over 3 minus 3y to the 5th over 5. We're going to evaluate this from 0 to 3. Okay, so hopefully you're still with me on this. Now I can simplify. So 27 over 3, that's going to give me 9. So this can be simplified to 9. And now we plug in the upper limit and lower limit. So we have 9 times 3 cubed minus 3 times 3 cubed, 3 to the 5th, I'm sorry, over 5. And lower limit will give us 0. So we could really just write this as, I guess we could simplify further. I think I want to leave it right here. So this is 9 times 3 cubed. I can write that as 27 minus 3 times 3 to the 5th over 5. So I'm leaving my answer right here, but it can continue to simplify if you wish to. All right, so we have made it to the last problem of this sample exam. So number 10, part A, evaluate this line integral. So we're looking at the line integral along curve C, y dx directly as a line integral, where C is an ellipse parameterized by these from 0 to 2 pi. Okay, so we're given the parameterization of our curve C. That's wonderful. So we just want to evaluate this line integral. Okay, so you should realize that this integral, you can also write it as the integral of m dx plus n dy. So you can realize it that way. So you know your field, so this is part A. So your field F has component m happens to be y, and n happens to be 0 since it's missing in the integral. Okay, so to evaluate this, we're gonna just go ahead and do that. So we're gonna first figure out the derivative. So let's write r of t first. So r of t, so c is described by r of t. Component wise, this will be 3 cosine t and 2 sine of t. That's what we're given. And we know t goes from 0 to 2 pi. So that means r prime of t will be negative 3 sine of t and 2 cosine of t, which means you know that this is going to be partial. This is the derivative respect to x. This will be the derivative respect to y. So dx dt or dy dt. You can think of it that way. So that means our integral, so the line integral along curve C of y dx, this is going to be the integral from 0 to 2 pi of y of r of t. So we're going to plug in the function, what is y. So y is going to be right here. This is our component y, this is our component x. So you'll have 2 sine of t times dx. Well, dx, as we said, this is the term dx, dt, so that would be -3 sine of t dt. That's how you set up this integral. And then you evaluate this, so not so difficult to do. So this is negative, I'll pull out the 6 times the integral, 6 times the integral 0 to 2 pi of sine square of t dt. And to evaluate this integral, we need to use an identity. So this is -6 times the integral from 0 to 2 pi of 1/2, 1 minus cosine of 2t dt. And then as we proceed with the integral, so every time you integrate cosine 2t respect to t from 0 to 2 pi, that's going to give you 0. So this integral will give you 0. So what we're really integrating is -3. So I pull out the half as well, from 0 to 2 pi of 1 dt. And as you integrate this, you'll get -3 times t. Evaluate it from 0 to 2 pi and plug in 2 pi, you'll have -3 times 2 pi, which will give you -6 pi. So the value of this line integral is -6 pi. Okay, now for the second portion of this, we want to apply Green's theorem to find the area enclosed by the curve C from part A. Okay, so we know that the Green's theorem, so for this portion, this is really the integral along curve C. This is a closed curve of f dot dr. So we're actually going to use the, this is going to represent circulation or work. So the Green's theorem for the integral along this closed curve C oriented counterclockwise of f dot dr, which is in our problem is the integral y dx. So this will be by Green's. This is going to be the double integral over the region R of n sub x minus m sub y dA. So that's by Green's theorem. So this statement right here, this is by Green's theorem. So let's go ahead and figure these out. So from the field, let's pick up. So from the field, we know our f happens to be y comma 0. So I'm going to just go ahead and pull that right here. So we know this is m and this is n. So let's go ahead and do that. So we know the value of this integral. This we got -6. So I'm going to substitute that. So -6 pi is equal to the double integral over the region R n sub x. So if I take the partial of this respect to x, well, that's going to be 0. So we have 0 minus partial of m respect to y. If I differentiate this respect to y, I get -1. Sorry, I got 1. So times that negative dA. So then this is going to be -6 pi is equal to, you can pull out the -1 times the double integral over the region R dA. And this is really just area. So we know that this is going to be -1 times the area of the region R is equal to -6 pi, which means that the area of the region R is 6 pi. So that's how you evaluate this integral. All right, so we have made it to the end. I hope you're able to get all of them correct. I also hope I didn't make any mistakes. So if I did, if you see something didn't make sense, please leave a comment in the description box. I'll try to respond to them as quickly as I can. So hopefully you enjoyed. So I wish you all very well on the final. Take care and see you next time.